Let us continue with the group activity questions what we are discussing in the previous video. So this is the next question. So here we are asked to find what is the output voltage if the values of B1 and B2 are 1 and 0. Here it is given that the value of R1, RF and R is equal to 1 kilo ohms. So that is we have all resistors. Okay, the values of R is equal to 1 kilo ohm, and this is 1K. This is also 1K. So carefully observe that this looks like a R2R network, R2R ladder, but there is a modification to be done, or there is a now since it is not asked to correct the circuit, so by just simply assuming this as a R2R network, we can simply write the output voltage using the equation of R2R network and start writing the output expression. Carefully observe the resistor values and give the combination of input voltage as 1 0 and try to find out what is the equivalent circuit. So for that, it's always necessary that you should not be behind the equations, and you have to conceptually understand how the circuit works. So for this particular circuit, for a combination of B1 as 1 and B2 as 0, so let us rewrite this. I can see B1 is equal to 1 means it is a reference voltage of 2.5 volts. You can see B1 is made 2.5 and B2 is made ground. So we can rewrite this as an equivalent resistor 2R and 2R in parallel. So it will become R here, and we have that R is coming in series with this 2R. So we have a voltage V1 which will be applied to the non-inverting terminal of this amplifier having a gain of 2 here. So this is what is output voltage now. Output voltage is actually 1 plus RF by R1 into V1. So since RF and R1 are 1 kilo ohms, so the gain happens to be 2 here. The output voltage is 2 times the V1. If you can actually find out what is V1 is, this is the voltage at V1. This has 2.5 volts by potential divider. We can write the output voltage V1 as the voltage at this node V1 as 2.5 into 3. This is 2R plus R is 3 divided by overall resistance is 4R. So this happens to be this is not actually 7. Is it 7.5? Let me just find out how much is that value. Let me just make a small correction. So here we have the total resistance as 3R plus R, which is 4R. It is 2.5 into 3R by 4R, which happens to be 7.5 by 4. So since the gain is 2 here, so this is gain part. 7.5 by 4 is V1. Actually the output voltage is 15 by 4. This happens to be 3.75 volts. So once we have this is actually not the V0. This is actually the full V0. So this is not V0 here. So please make that correction. The output voltage is actually 3.75 volts. So here we have V1 as 7.5 by 4. That is multiplied by 2. So which happens to be 3.75 volts. So this way we can't simply use the equation of a R2R ladder and then use it for any given circuit. We need to carefully observe the changes in the circuit. Suppose if this was 2R and R, you would have directly written the output voltage as half of 2.5, that is 1.25 into 2 will be 2.5 volts. This would have been 2.5 volts if this resistor is 2R and if that resistor was R. Since there is a wrong connection or the wrong values of resistors are connected in the ladder, so this output voltage is different. Now let us try to find out in a 3-bit RDAC if the resistance of the switch is 100 ohm. We are asked to estimate the value of V0 when B1, B2, B3 is 100 and 001. We have been asked to take the value of R of that weighted R DAC as 10 kilo ohms once, and in the second case it is asked to take the value of that weighted resistance RF 100 ohms. So here also we need to be very careful. The value of R is given as 10 kilo ohms. So we have to actually know that this output voltage is given by K into V reference RF divided by B1 by 2R in general, B2 by 4R plus B3 by 8R. Now since there is a switch is included for all the resistors, we are writing simply 2R plus R switch, 4R plus R switch, and 8R plus R switch. So here it is given that for the first case, since the value of R is given as 10 kilo ohms, so here it is K into V reference into RF divided by B1 by, so 2R happens to be 2 into 10K, which is 20K plus 100 ohm. So B2 is B2 divided by 4R, since R is equal to 10K, it is 40K plus 100. So this is 80K plus 100. In the general expression, when the on resistance was neglected, we have actually written this as RF by R, and this is B1 by 2, B2 by 4, and B3 by 8. We can't use that equation because we are including the effect of that switch resistance. So we need to modify the final expression what you have derived it for a weighted R network or DAC. So we can't directly use that. So we need to correspondingly adjust the equation. Now it is now 2R plus switch, 4R plus switch, and 8R plus switch resistance. Now upon applying this combination of the input voltage as 100, so this is what the combination of the input voltage, which is 100 here. This is for a combination of 100. We have this as 5 is the reference voltage, 10K is RF, and K is equal to 1. So since it is 100, only B1 is 1, other two are 00. Now it is 1 divided by 20K plus 100 ohms. So this happens to be 2.487 volts, whereas expected is 2.5 volts. So we can see there is no too much of a variation because the switch resistance is very small compared to the resistance R. So because we have taken R is equal to 100 ohm, the switch resistance is 100 ohm, and the value of weighted resistor R is 10 kilo ohms. So if you actually do the same for the same combination, if you consider the resistance as 100 ohm, the R is equal to 100 ohm and the switch is 100 ohm. It's not actually 16.66, is actually 1.66. Let me make that correction. By considering the R value as 100 ohm and the switch resistance as 100 ohm, since switch resistance is comparable to the resistance, almost equal to the R value, we are actually expected 2.5 volts for the MSB as 1, but we are getting it as 1.66. You can see the error is too much. When the value of R is equal to 10 kilo ohms, the error was not too much. So when we have the switch resistance comparable to the weighted resistance, the error is too much for the MSB here. Let us redo the same thing for 001. Actually this 1.66 is for MSB, not for the LSB. So we are redoing it for the MSB here. So sorry, the LSB value. For LSB, if the value of B3 is now actually 1. So B3 is 1, now it is 00, and it is 1 divided by 80K plus 100 ohm. So it was supposed to be 0.625. We are getting very close to that. So there is no much error. So let me just correct this value now here. Now you can see for the same LSB portion of 00 for LSB bit as 1001, when the value of the R is equal to 10 kilo ohms and the switch resistance is 100 ohm, we were expected 625 millivolts as the ideal value. Because of this inclusion of that resistance of the switch, we are getting very close to that, meaning since it is too far away from 80K, there is no much effect of that. So let us try to see what is the effect of reduced value of R, which is now the R switch is now coming comparable to that 800 ohm. So in spite of this having very close to this, you can see the amount of variation is not too much. So here we are expecting 625 millivolts, but we are getting 624 millivolts, which is not too far away from the error from the expected value. Error is not too much for the LSB. The whole idea of trying to do this problem is, so the switch resistance will going to affect the most when the value of the resistance is less or it is comparable to the switch resistance only for the MSB bit. So only when the MSB bit is 1, we'll have too much of error. So we are supposed to get it as 2.5 volt, we are getting it as 1.66. You can see we are supposed to get it as 625 millivolts. We are getting almost 625 millivolts because now this is corresponding to LSB, this is corresponding to MSB. The whole idea is the switch resistance will affect the most if the bit is 1 at MSB level. So these are the things we need to keep in mind whenever we are discussing this DAC circuits. So the weighted R, the most disadvantaged thing is that the value of the resistance is keep on exponentially increasing as the number of bits increases.